All right, today we're going to tackle one of the most important ideas in all of computer science, the tree data structure. You might not see it, but it is everywhere. It's kind of the invisible backbone of our digital world. So let's dive in. So think about this for a second. How does your computer find that one file you're looking for instantly? I mean, you've got thousands, maybe millions of files, and boom, it's right there. It feels like straight-up magic, right? Well, it's not magic. It's just really, really smart organization.
And the secret to that organization? It's a powerful idea called a tree. And honestly, you already know what this looks like. Just think about your computer's file system. You've got folders inside of other folders, and files inside those folders. That whole structure? That's a tree. You use one every single day.
Okay, so what is a tree, really? I mean, from the computer science point of view. Let's break down the official blueprint.
Okay, I know, that sounds super formal and maybe a little confusing, but the idea is actually pretty simple. You have one starting point, which we call the root. Then everything else just branches off from there. Think of it like a family tree. You have parents, you have children, and these smaller branches form their own little sub-trees. The whole point is to organize things in a hierarchy.
To really see why this is so special, let's put it next to something we all know, like a simple list. A list is, well, it's a line. It's linear. One thing comes after another. A tree, though, is nonlinear. One item, we call it a node, can be connected to many other nodes. And that one-to-many relationship, that's the secret sauce. That's what makes trees so powerful.
All right, let's get some basic lingo down. The root, that's the very top, where it all starts. A node is just any point, any item in the tree. And a leaf? That's a node at the very end of a branch. It doesn't have any kids. So, root, node, leaf. Simple enough, right?
Now, there are a ton of different kinds of trees out there, but the one you'll see most often, the real celebrity of the tree world, is the binary tree. So let's take a closer look at what makes this one so special.
You know, the rule for a binary tree is almost elegant in its simplicity. Every single node can have, at most, 2 children. That's it. 0, 1, or 2. We just call them the left child and the right child. And this one little rule, it unlocks a crazy amount of efficiency. You'll see what I mean in a sec.
Okay, so how does this whole power of 2 thing actually help us find stuff super fast? Well, that brings us to a special version of the binary tree called the binary search tree, or for short, a BST.
This is the whole trick. The BST has one more rule, and it is everything. For any node you pick, everything to its left is smaller than it, and everything to its right is larger. Left is less, right is more. That simple ordering is the key to its incredible speed.
Okay, let's walk through an example. Say we're looking for the number 13. We always start at the root, which is 10. Now, is 13 bigger or smaller than 10? It's bigger, right? So we know it has to be on the right side. We just completely ignored the entire left half of the tree. Cool. So we move to 15. Now, is 13 bigger or smaller than 15? It's smaller, so we go left. See? Another chunk of the tree gone. We're at 12. Is 13 bigger than 12? Yep. Go right, and there it is. Found it. In just a few steps, we sliced away huge portions of the data we didn't need to look at.
And that's the whole magic trick right there. Instead of plodding along, checking every single item, we make one simple decision, bigger or smaller, and we chop our search problem in half every single time. It is just unbelievably efficient.
But it's not a perfect system. There's a catch. This amazing speed has a huge weakness. The whole structure can, well, it can basically fall over and lose all its power.
So here's a question for you. What do you think would happen if we tried to build one of these trees, but we added the numbers in perfect order? Like we add 1, then 2, then 3, then 4, and so on. What would that tree look like?
Well, you'd get this. On the left, you see a nice, healthy, balanced tree. It's bushy, it's spread out, it's fast. But on the right, that's what happens when you add sorted data. You get a degenerate tree. It's just a long, pathetic, spindly chain. I mean, technically, it's still a binary search tree, but it's completely lost its superpower. Searching this thing is no faster than just checking a plain old list one by one.
And that's the Achilles heel right there. An unbalanced tree makes that amazing speed advantage we were just talking about completely disappear. So the big question is, how do we stop that from happening? The solution is honestly pretty genius. What we need is a tree that's smart enough to keep an eye on its own shape. a tree that can notice when it's starting to get out of whack and fix itself.
And that brings us to these more advanced data structures called self-balancing trees, like the AVL tree. You can just think of it as a much smarter binary search tree. It's got this built-in supervisor that's constantly checking to make sure it doesn't get all lopsided and slow.
So how does it do that? Well, the AVL tree keeps track of something called a balance factor for every single node. And all that is the height of its left side compared to the height of its right side. An AVL tree has a very strict rule. That difference in height can never be more than 1.
And here's the cool part. If adding or removing a node ever messes things up, if that balance factor hits 2 or -2, the tree automatically triggers what's called a rotation. It literally just shuffles a few nodes around to get back in balance. This way, it guarantees it always stays bushy, efficient, and most importantly, super fast. So where are these amazing structures hiding in plain sight? Well, pretty much everywhere. They're in your 3D video games, helping figure out what to draw on your screen. They're in the internet routers that are sending you this very information right now. Compilers use them. Your MP3 and JPEG files rely on them. Databases are indexed with them. And yeah, like we said at the very beginning, your computer's file system is built on them. They are, no exaggeration, a cornerstone of how computers work.
So from finding a simple file to rendering your favorite game, it makes you wonder, doesn't it? Just how many of these invisible, elegant trees are working behind the scenes right now just to organize your digital world? Something to think about.